So today we are going to continue our lecture on the theory of structures, and we are going to look into a new method to analyze your indeterminate structures. That is the second method that we will learn in this lecture. We call it the moment distribution method. And if you remember in our first meeting for our class, I have mentioned that there are some questions which is compulsory for you to answer during your exam time, and which is some question you can choose whether to answer them or not. One of the compulsory question for your exam is the moment distribution method. So like it or not, then you have to choose. You have to answer this question when it is asked in your exam time. And the moment distribution method also actually contribute the maximum mark for question in your exam. If other question is, I think, around 25%, moment distribution is, I think, 34% for your final exam. So you will also have more time given to answer your question for moment distribution method. So I hope you will give more attention for this method. It is not difficult in my point of view, but since it has more small steps, then students sometimes they make mistake in this one small step, and this one more small. If you make mistake in one of the steps, then definitely you couldn't get the final answer correct. And I also have seen a lot of students which is very good, and they have answered it very well. If they but only one parameters in the analysis was wrong, then the whole answer also was wrong. So for this moment distribution method, there are 6 steps that you have to do one by one. I listed it here in order for you to just go back to this slide anytime you wanted to do your exercise in moment distribution method. This way you will not forget what you have to do, next in the method. So I will explain to you in detail in my next slides, but just to give you an overview, for this moment distribution method, we have 6 steps. The first one, you have to calculate member and joint stiffness, and the second one is the distribution factor for all the members at the joint. So I highlighted here, you have to calculate the member and joint stiffness first, and also distribution factor, and after that the carryover factor. And you have number 4, you have to calculate the fixed end moment, or if any settlement happen, you need also to calculate the moment due to support settlement. And this one, step number 4, is exactly the same like the one that you have already learned in your slope deflection method. So there is no differences. And number 4, it's actually what we've already learned so far. And after you have calculated all 4 parameters, or the 4 steps you have already completed, then you have to prepare a distribution table. And this distribution table depends on the number of real supports. So if you have 4 supports and your main column is going to be 4, if you have 3 supports, then your main column will be 3. And after that, you just have to add all the numbers in the column. So anytime you are doing moment distribution method, go back to this slide in order for you to remind yourself what you have to do. Okay, but of course, right now it doesn't make too much meaning if I say to you all the 6 steps before we look into it in detail. So I take back the example that we have already solved using the slope deflection method, the first method. So in this example, you have a continuous beam which is have the cantilever at point A with 2-meter span between point A and support B. And support B is pin support. Support C is also pin. And support D is a fixed support. And you have 30 kilonewton point load at mid-span of span C and D. And you have also 10 kilonewton meter uniform distributed load for span BC. And this one is 4 meter, this one is 2 meter, and the material properties for your beam are all the same, so you have EI. And for the first example, we are going to do for the beam without settlement. So you can compare both methods, which one you feel it is more easy. Some students think that this method, moment distribution method, is easier for them, and another students think that this slope deflection method is easier. But personally, I think if you do it very careful, moment distribution method is easier. You will see what I mean, okay? Because it doesn't involve any detailed too much calculation. However, it's just a simple, small calculation that you have to be very careful. Now, the first step that we have to do is to calculate member and joint stiffness. So this one, you have to actually calculate the K. If you see in your mechanic of material, you learn about calculating K, the stiffness of the element. So in here, you're going to use the same concept in order to calculate for your member and the joint stiffness as the first step. So if I have this type of beam, a continuous beam, what you have to remember is that this that I have already highlighted the guidance for you. The guidance in here is that if the member is one end cantilever, so it is going to be K equal to 0, the stiffness equal to 0. And if the member is supported by one end pin and one intermediate pin support, so the stiffness is going to be 3EI over L. And if the member is supported by two intermediate pin support, then it's going to be K equal to 4EI over L. And if the member is supported by one fixed end, then it's also going to be 4EI over L. So this is the member stiffness that you have to first calculate. I repeat, if it is one part of the member is a cantilever, then it is for cantilever structure, it is K equal to 0. If it is one end supported with end pin or end roller, then it is going to be 3EI over L. And if it is both supported by pin support, intermediate pin support, then it's going to be 4EI over L. And if it is one fixed, then it's going to be 4EI over L. So you have actually only two equations that you have to remember, is that one is 4 and in another one is 3. So either it is 4EI or 3EI, or there is no stiffness at all. Now, if I calculate the member stiffness for KAB, so this one is A, this one is B, and this one is C. Sorry, this is just the what I mean is this one. Okay, this is the not our example, but this is the guidance, and this we are referring to this one. Now, if I want to calculate the stiffness for member AB, I should put it in the notation of KAB. So this is the stiffness of member AB equal to 0. And if I want to calculate the stiffness of member B and C, so I have to put it KBC equal to 3EI over L, because this is the end support. So 3EI over L, EI is what you have already been given in your example. So it depends on the material properties of your beam. If this is 2EI, then you have to put it in your equation as 2EI. If this is a 3EI, then again you have to put it in your equation as 3EI. So it depends on the material properties of your structures. Now, for KBC, 3I over L, L is 4 meter, right? So this is 2 meter, 4 meter, and 4 meter. So this is 2, so this is 4 meter, and this is 4 meter. This is why we have 3 EI over L, and this is the value equal to 0.75 EI. And for member stiffness CD is going to be 4 EI over L because it is supported one end with the fixed support and another with the intermediate pitch support. So you have 4 EI over L and 4 EI over 4. So you will have equal to EI. Now I mentioned here if the member has 2 EI, so you have to do it like 4 times 2 EI over L. So it depends on the method properties given to you. Now after I calculate the member stiffness, I have to calculate the joint stiffness. The joint stiffness is when I'm looking at this one. Okay, so you have 1 joint, 2 joint, and 3 joint. And what is the joint stiffness? Joint stiffness is the total stiffness of all members attached to it. So for joint B, I have member AB and member BC. So for joint C, I have member BC and member CD. And for joint D, I only have one member attached to it, is member CD. So now I can easily calculate what is my joint stiffness. So for joint stiffness KB is actually the summation of KAB plus KBC. I just use the values that I have already calculated in here. Okay, into my equation. So I will have the joint stiffness of joint B is going to be 0.75 EI. For joint C, KBC plus KCD, because this one, so joint C, I have one element over here and another one element over there. So I have 2 members attached to it, so KBC plus KCD. I just use the value that I have calculated, and I have my joint stiffness to be 1.75 EI. And for KD, I have a KCD, a KDC for one member, and another one is attached to the wall, so stiffness of the wall. And the stiffness of the wall is infinity, so the total stiffness for KD is going to be equal to infinity. So this is what I have. Okay. Now I can go to the second step. So the second step is to calculate distribution factors. The notation is DF, distribution factor. Equation for distribution factor is stiffness of the member divided with stiffness of joint. So you can see here, whatever values that I have calculated in here, member stiffness and joint stiffness, I will use it back in my second step, that is the calculation of distribution factor, stiffness of the member divided with stiffness of the joint. Now what I'm going to do is that I have to look into it joint by joint, because for each joint I need to see the distribution factor of all members attached to it. So if I have joint B and I have member AB and member BC attached to it, so I need to calculate distribution factor for BA and BC. And if I have joint C and the member attached to it for joint C is member BC and CD, so I have 2 distribution factor CB and distribution factor CD. And for joint D, I have only one member, that is member CD or DC here. So I have to calculate the distribution factor of DC. And in order for me to calculate each of these, I refer to this equation, stiffness of the member divided by stiffness of the joint. So stiffness of the joint always referring to the joint that you are that you are considering. So for joint B, always I have here KB, KB, and for joint C, I have KC, KC, and joint D, I have divided with KD. And for the member of the joint is the member of the distribution factor that you're considering. So for this one, distribution factor for BA, so I need to have stiffness of member BA divided with stiffness of joint B. Stiffness, the distribution factor of BC, I need to take stiffness of member BC divided with KB. And this one, KBA, KBC is all that I have already calculated over here. KBA, KBC, KCD. So just for your information, there is no difference with KBA or KB. For example, this one KBC, so it is going to be the same with KCB. Okay, so it's just the notation because it is the same members. So now I just include all the values that I have already calculated before this for each member. So for joint C, distribution factor of member CB is going to be KBC divided by KC. So KBC, I have already calculated this one, KBC 0.75 EI and KC 1.75 EI. So this is where I got it, 0.75 EI divided by 1.75 EI, and I will have 0.428. Now I go to the other member, that is the member CD for this joint. Okay, so member CD. So I have the stiffness of member CD divided with the stiffness of joint C. Now I have KCD divided by KC. So KCD I have already calculated to be EI and KC 1.75 EI. 1.75 EI. So I have this one equal to 0.572. Now bear in mind that the total of distribution factor for each joint should be equal to 1.0. Okay, so these two, okay, you have to total it up to be 1, and this joint B also it equal to 1. For the stiffness for the fixed end, since you have to divide it with infinity, so it's going to be 0. Okay, so this is the steps to this calculation of distribution factor, and these are all the steps that you have to do. So as you can see, there is no new equation. You just have to use whatever values that you have already calculated in step 1. Now in step 3, there is also no calculation. You just have to remember only two values. Carryover factor either is going to be 0.5 or it's going to be equal to 0. What is the difference between the 0.5 or 0? Is that if the moment can be carried over, C will be equal to 0.5. And if the moment cannot be carried over, C is going to be equal to 0. Now, what does it mean? If I have N pin I have a continuous beam which is supported with N pin at the end, intermediate pin, and also a fixed end at the other end of the beam. So from B to C, if I have a moment that I calculated on B, this moment can be carried over to C because intermediate pin can store that moment temporarily. So in other words, from N pin support to intermediate pin support, the moment can be carried over. So when the moment can be carried over, the C is going to be equal to 0.5. Okay. From support C intermediate pin to fixed end, the moment can be carried over because the fixed end can store the moment. So when the moment can be carried over to the other support, it is 0.5. Okay. How about from the fixed end to intermediate pin? Although intermediate pin can take the moment, but you have to remember there will be no moment that can be carried over from a fixed end. So fixed end will keep all the moment to itself because it is a strong connection, so it doesn't share. In other words, like it doesn't share the moment to the other support. So when you have a fixed support, there would be no moment that can be carried over from a fixed support. So it's going to be 0. Okay, so from fixed to pin is going to be 0. And how about from intermediate pin to an N pin? N pin couldn't store, couldn't have, will not have moment because N pin doesn't restrict the movement of your beam in the rotational movement, so cannot carry over because N pin cannot store the moment. So from intermediate pin to N pin is also going to be 0. Now this is only the thing that you have to remember. So the carryover from B to C is going to be 0.5. Carryover from C to D is going to be 0.5. However, for carryover D to C, okay, carry over D to C is going to be 0, and carry over from C to B from C to B also is going to be 0. So this is the third step. You just have to look into the connection, whether moment can be carried over or moment couldn't be carried over. The simple guidance is that for fixed support, it will not share the moment, but it will take the moment. So if you have any fixed support, always the carryover to the next support is going to be 0, but carryover from any support to fixed end is going to be 0.5, and the end pin will not have moment at the end of your calculation, so it will not take any moment into it, but it will distribute the moment to the other connection from the end pin. So from end pin to intermediate pin 0.5, but intermediate pin to end pin is going to be 0. Now this is the third step. You can see that it is very straightforward. Either it is 0.5 or 0. And the fourth step is the fixed end moment. Fixed end moment is the one that you have already understood, or you have already learned from your previous method, the slope deflection method. So it's going to be all similar method, and you have to calculate for each member. So we have member AB. For our example, we have 3 members. Member AB goes back. Okay, so we have member AB, member BC, and member CD. So we calculate this one first, and then the second one, and then the third one. Okay, so this is where we are. The first one, member AB. So for member AB, it is one end as a cantilever end with axial load pointing downward of 5 kilonewton, and since it is pointed downward 5 kilonewton, so our beam is going to be deflected using this angle. In other words, your theta is going to be counterclockwise. So in order to push back this member to this original position, you need to introduce another one moment, what we call the fixed end moment, FEMBA, that tries to push back your member to this original position. So the direction is going to be clockwise direction, because it's trying to push it backward. Now, since it is the clockwise direction, so it's going to be positive, right? And the value is going to be the axial load times the moment arm. So 5 times 2 is going to be 10 kilonewton meter. Now you have FEMBA. For member BC, also the similar method that you have already calculated before. You have the uniform distributed load, 10 kilonewton per meter, and due to this 10 kilonewton per meter, your deflection of the beam is going to follow this curve. In other words, at the end of your E support, you have the deflection of clockwise direction. So the job of your fixed end moment BC is going to try to push it back to the original position. So it's going to have a counterclockwise direction. So this is FEMBC. And on the other hand, since you have a counterclockwise deflection over here, so the fixed end moment tries to push it back to the original position. So that's why you have a clockwise direction for your FEMCB. Now this is why for FEMBC you have negative, and FEMCB you have positive, because it is clockwise direction. For the equation of uniform distributed load, it's WL square over 12. So W is here, 10 kilonewton per meter. L is the length of your structures, of your beam, and 12. You solve this equation, you will have negative 13.33 kilonewton meter. And you solve this equation, you will have positive 13.33 kilonewton meter. And for member CD, you have a point load 30 kilonewton at midspan of member CD, and due to this pointing downward point load, your deflection of the beam, of course, is going to follow this direction. So this is the deflection angle, and the job of your fixed end moment at the end of CA is going to try to push it back to the original position. So you will have a counterclockwise. Since it is counterclockwise, you will have negative over here. right? And at the other end, FEMDC try to push it back to the original position, so it's going to be clockwise direction. That is why you have a positive direction, a positive moment over here. And the equation is going to be PL over 8. So P is the point load. Okay, P is here, L is the total length of your member. It's going to be 4 meter and divided by 8. So you will have negative 15 for FEMCD, and you will have positive 15 for FEMDC. Now you have all the end moments that you need to proceed with your calculation. So you have already completed step 4, and the step 5 is actually to put everything in your distribution table. Now this distribution table is the main job for your moment distribution method, because everything has to be calculated on your table. But when you see here, it's going to be too much information for you. We are going to look into it one by one, and you will see that it is also very straightforward. What you have to do is that you have to first create your table column. So the first column is and just the information that you need to have, and also the first row is the join. Since right now we have 3 main support, so this is why our column has 3 main columns. Our table has 3 main columns, so this is going to be based on your support. So you have the main column number 1 is for joint B, and main column number 2 is for joint C, and main column number 3 is for joint D. So on the other end, I put here is the joint. Okay, so do you know that this is for joint? So you have joint B, C, and D. Now the next row is for you to include all the members which is attached to that joint. So for joint B, if I draw it just to, so you have actually something like this. Okay, you have B, you have C, and you have D, and we have a 30 kilonewton over here, and you have uniform distributed load, and you have a point load on our cantilever A. So this is what we have. And for joint B, what the members attached to it is member BA. Okay, this is where I put BA, and member BC. So this is where I put BC. And for joint C, member attached to it is member CB and member CD. So this is where CB and CD. And for joint D, there is only one member, that is member DC. So this is where we have DC. Now distribution factor that you have already calculated from step 2, you just have to include it in here. So let us see all the distribution factors that you have already calculated for BA, BC, CB, CD, and DC. So you just have to take it back over here. So let's see, just to, okay, this is the step 2 that you have calculated distribution factor. So distribution factor for BA is 0, BC is 1, CB 0.428, and CD is 0.572, and DC is 0. So this is where we got it, distribution factor 0, 1, and this value, and this value, and this value, right? And we have also the carryover factor. So this carryover factor also is what you have already calculated before, you have already determined before. This is the carryover factor. So from B to C is 0.5. For this one is the guidance. So you can see for our example in here. So since this is the end pin to intermediate pin is going to be 0.5, because it can carry over 0.5 over here, and from C to D also it can carry over, so it's going to be 0.5. However, from D to C it will not carry over because D is a fixed support. So from here to it's going to be 0, and from C to B also it's not going to be carry over because B is the end pin, so it's going to be 0. Now you can have, so this one is 0.5. Okay, so here for the carryover, of course, for B to A is going to be 0 because it's cantilever, and from B to C is 0.5, right? 0.5, and from C to B to B is 0. So this is why I put 0. And from C to D is 0.5. So this is why I put 0.5. And from D to C is going to be 0. So this is where I put 0. So now you just put all the carryover factor over here. And you have also the fixed end moment that you have calculated. So for BA, how much is the fixed end moment? BC, you put it back, CB, CD, and DC. And this one also you have already calculated in here. So this is BA, positive 10. And this is BC, negative 13.33, CB, positive 13.33, CD, and DC. So you just have to take all this value and put it inside your column. Okay, so I have positive 10, negative 13.33, positive 13.33, negative 15, and positive 15. So until now, until this level, okay, upward is all that you have already calculated in all your steps. So you have step 1, 2, 3, and 4. So this is all the information that you have already done. This next step is to just do some balancing carryover of inside this table. That is also going to be very straightforward. Now let's see what you have going to do next. So for this one, the first thing that you have to do is to look to balance the moment for each joint. Okay, so you knew that in each joint that we have already learned before, you have to maintain the equilibrium of moment on that joint. In other words, that the total moment in that joint has to be all equal to 0. It has to be balanced. So for this one, for joint B, okay, if I have this fixed end moment, positive 10 and negative 13, in order to keep this one as all in total balance as a 0, I need to introduce one moment, okay, for these two, since the difference between these two moments is going to be negative. Okay, so negative 13.33, positive 10, then the difference is going to be negative 3.33, right? So in order to balance this one, I have to introduce one moment to balance this. So I will introduce positive 3.33 moment, positive 3.33 moment, and the distribution is going to be based on the distribution factor. So for each member, I need to distribute this newly introduced moment based on their distribution factor. So if I have 3.33 in here, 3.33 in here, so this 3 moment, 1, 2, 3, okay, it's going to be equal to 0, right? So I need to balance it. So distribution factor for BA is going to be 0. So this is why I times it 0. And distribution factor for BC is 1. So I times it 1. So in other words, this one is going to have 0, and this one is going to be 3.33. So if you calculate back this one, and this one is going to be 0. Okay, so I stop for member B, joint B. I go to joint C. And for joint C, I have positive 13.33 and negative 15. So these two, the difference is going to be negative 1.67. So I need to introduce a positive 1.67 in order to balance this connection. So in order to balance this one, this positive 1.67 should be introduced in here and times the distribution factor of each member. So I have 1.67 positive times the distribution factor of CB, this one, 0.428, times the distribution factor of CD is going to be times 0.572, and I have this value. So if I calculate back this one times this one times this one plus this one plus this, and this is going to be 0. Now I have a fixed end moment of 15, positive 15 for DC, and distribution. So distribution factor is going to be 0, so it's going to be 0 over here. Now, after I have balanced it, I need to carry over this method to the joint that can take the moment. So so I start with this one, 0. The carryover for B to A is going to be this one. So it's going to be 0. So this is why I got 0 to 0. Okay, carry over. So it's going to be here, right? And so for this one, is going to be, sorry, I made a mistake. You shouldn't carry over. This one is the same element. It's going to be from B to C. Okay, so B to C or C to B. So for this, carry over from B to C is going to be 0.5. So I have to take all this one and see where it can be carried over or where it cannot be carried over. Okay, so from B to C, my carryover is 0.5. So this is where I take this one, carry over 0.5. So 3.33 times carry over 0.5, I have this amount. And for this one, carry over from C to B is 0. So this is why this one to this one, carry over 0. Okay? And from this one, I have C to D. C to D is 0.5. So this is where I have what I have here, C should be carried over to D, 0.5. So C 0.96, I carry over half of D to the support D. However, for support D, I don't have any carryover, so this is why it is called 0. Okay, so this one is 0.5 because they carry over here 0.5, and this one is 0.5. This is why I get 0.5 over here. Now, after I have carry over, right now I have a new moment over here. Okay, 1.67, and this one is 0.48. So if I see for this one, I don't have to balance it anymore because all is already 0. However, for joint C, since I have a positive 1.67, in order to balance this moment, I need to introduce one negative 1.67 moment. So this negative 1.67 moment, I need to distribute it to the member based on based on their distribution factor. So I have negative 1.67 times 0.428. So this is why I times 0.428 because of this. So it will be negative 0.71, and I have negative 1.67 times the distribution factor of CD. Then I will have negative 0.96. So this one's distribution factor is always 0, so I have 0 over here. Now, once I have this moment, again, I need to carry over them. So for this one, carry over from B to C is 0, so I don't have anything to carry over, so it's going to be 0. And from this one, carry over to from C to B is 0, so this is why I got 0. From C to D, carry over 0.5. So this is why from C to D, I have this one, negative 0.96 times 0.5. So I have this amount. And from D to C is 0. So this is why I got 0. Now, when to stop? Okay, so the point of stopping is that when you in your exam is that when the carryover all the moment is equal to almost 0. Okay, so for example, in here after 2 times of balancing, my moment is almost 0 for all members. So this one is 0, 0, 0, 0, 0, and I have around negative 0.48 in which I say I can neglect them. However, in your exam, there might be a condition where after 3 times of balancing and carryover, you still have some moment over here. So after 3 steps, you can just stop. There is, of course, your final answer is going to be having some error of a small moment of error, but we accept your answer after 3 balancing and carry over, because you do not have too much time to just carry over and balancing until more than 3 steps. So after 3 steps you can stop, and when you stop over here, okay, so this is the time when you just have to calculate, or you have to just sum up all the moments that you have already calculated. Now bear in mind that it should start from here. Okay, so it starts from here and downward. So you have a fixed end moment of positive 10. What you did is that you just have to sum up everything. So you take this one, positive 10, 0, 0, 0, 0. That's why you got positive 10. Now you have here negative 13.33 plus 3.33 plus 0 plus 0 plus 0. This is why you have negative 13.33 plus this one, you have negative 10. And from here, you have this positive 13.33 plus 0.71. This is why plus 1.67, this is the one, minus 0.71, you get positive 15. And another member, for member CD, you have negative 15 plus this one minus this one, so you will have a total of negative 15. Now you have also positive 15, positive 0.48, negative 0.48, so you total everything, you get a positive 15. So this is the end moment that you have already calculated. You have positive 10, negative 10, positive 15, negative 15, positive 15. So if you can see back, it is the same end moment that you have calculated using the slope deflection equation. However, for this method, you do not need to come out with your slope deflection equations, and you don't have to do all this solving to get theta B, theta C. You just have to do your table, but be very careful with the parameters. Then you can get your end moment of BA, BC, CB, CD, and DC. And if you put it inside your calculation, it's going to be BA positive. So BA positive is going to be 10. And you have BC negative 10. So negative 10 is going to be counterclockwise 10. And you have a CB positive 10, a positive 15, so CB positive is going to be clockwise direction 15, and you have DC, CD negative 15, so negative 15, and you have DC is going to be positive 15, so positive 15. So this are all the end moments, and once you get the end moment, then the procedures also is going to be all similar with the one that you have already calculated before. With this end moment, you analyze it part by part in order to get what is the support reaction RB, what is the support reaction RC, what is the support reaction RD, and with all these things, again, you do your shear force and bending moment diagram. So up to this stage, is going to be a little bit different, and after this stage the procedures are all going to be similar with your slope deflection method. Okay, all right, so basically that's the whole procedure that you need to go in order for you to use your slope deflection method, your moment distribution method. Up to here I will open for any question. In this example, we have a beam similar to the one that you have already solved using the slope deflection method, and also similar to the one that we have already solved before. And the difference with this example is that it has a settlement. So in this beam, support C settled in the downward direction of 20 millimeter. Okay, and the other parameters, the other loading condition and support condition are all the same with the previous example. And it is also only due to this settlement that what will change is your step 4. So the other steps that we have already learned before, this joint stiffness, member stiffness, distribution factor, carryover factor is going to be the same, because the condition of the beam, the material properties of the beam, and the support condition is the same with the previous example. Since there is only additional of settlement in this example, so the only difference is going to be your step 4, that is the fixed end moment, and that is the moment due to the support settlement. And for moment due to support settlement, the calculation also is going to be similar with the slope deflection method that you have already learned so far. So the moment due to support settlement of BC is going to be following this equation, negative 6EI delta over L square. So the only difference here is the delta that you have to be careful. So if this support settled 20 millimeter downward, the deflection of the beam is going to follow this direction, right? This mode of settlement. In other words, closer to support B, the settlement, the deflection is going to be clockwise direction, and closer to support D, the deflection is going to be counterclockwise direction. Now, if it is for member BC and also from the end of CB, it's going to be still like this one. Clockwise direction. This is counterclockwise until here is counterclockwise. So if the delta is is a clockwise direction, so it's going to be a positive delta. If it is counterclockwise, it's going to be a negative delta. Okay, so you just have to put this value of settlement 20 millimeter in your equation and be careful with the positive and negative sign. So if here for MSSBC, for BC is going to be positive. So it's going to be positive 0.02 for the delta. And if you solve this equation, you will have negative 60 kilometer meter. Similarly, for MSSCB is going to be a negative 60 kilometer meter. Okay, because it is still the clockwise direction. From the other end of your member CD is going to be counterclockwise direction, so it's going to be negative. So this one is going to be negative 0.02, and if you include in your equation, you will have positive 60 kilonewtons. Similarly, for MSSDC, you are going to have positive 60 kilometer meter. So this value is the one that is going to be added in your column. Okay, only this one. So your column will be similar. So you have joint B, C, and D. And for the second row, you have to write down your members. So for joint B, you have member BA and BC. For joint C, you have CB, CD, and joint D, you have DC. And then you have your distribution factor. Distribution factor is going to be 0, 1, 0.428, 0.572, and 0. So until this one, and the carryover is going to be similar with what we have already discussed so far. And the finite, the fixed end moment also is going to be similar until here, positive 10, negative 13.33, positive 13.33, negative 15, positive 15. So until here is the same. Okay, until here is the same with the previous example. Now the only thing that we add is the moment due to support settlement, in which the moment due to support settlement for BC is negative 60, CB also is going to be negative 60. So this one, BC, negative 60, CB, negative 60, CD, positive 60, and DC also positive 60. So this is where you have it. Positive 60, positive 60, negative 60, negative 60. Now, until here, it's all similar, but since you have two moments for this case. One is the fixed end moment, and one is the moment due to support settlement. You first need to sum up these two moments first, okay? For your calculation, sum up these two moments. So positive 10 and 0 is going to be positive 10. Negative 13.33, negative 60 is going to be negative 73.33. So I sum up these two. I will have negative 46.67. Sum up negative 15 plus 60, I have plus 45, and positive 15, positive 60, I have plus 75. Now I keep this one, and this is the time, this is the point that I have to do my calculation onward. So remember I mentioned to you that in your this one, you have to take in the end, in order to get this value, you have to start from here, positive 15 in here. So for this one, if you have two moments due to moment settlement, you have to sum up everything first, and please be careful, you start from here, okay, downward. Now, in order for me to balance this moment over here, I have to use the same method that I have. I look into the joint per joint. So for this joint, I have to balance them. If I have positive 10 and negative 73.33, in order to balance this, I have to introduce a positive 63.33 to balance this addition of negative 63.33. So this is why I have positive 63.33, positive 63.33. 27.33, and the distribution is going to follow the distribution factor for the member. So for this member, distribution factor is 0, so I times 0. This one, distribution factor is 1, so I times 1, so I have this thing. And for joint C, I have these two values. And I sum up these two values, I have an additional negative 1.67. So in order to balance that negative 1.67, I have to introduce a positive 1.67. Positive 1.67, and to distribute it, I use the distribution factor 0.428 in here, and in here 0.572. So I times this one, I have this value. Now this one distribution factor is already 0, so I have 0. And after that, I have to carry over. So carryover factor from B to C, okay, B to C is 0.5. So this is where I got it. I use this one, carry it to B to C, 0.5. So 0.5 of this, 63.33, I take it to C join. And from C to B is 0. So C to B is 0. And from C to D is 0.5. So C to D is 0.5. And D to C is 0, so it's 0 in here. Now in the end, I have this value 31.67, and this one. So I have to balance the joint. So this for joint B, there is nothing to balance because it's already 0. But for joint C, I have 31.67 positive, so I need to introduce a negative 31.67 and distribute it using the distribution factor times 0.428 times 0.572, so I have this one, and this one is 0. So due to this new moment, I have to carry over. So carry over B to C is 0.5, but there is nothing to carry, 0, so 0 in here. And carry over from C to B is 0, so I carry over 0 in here. Carry over from C to D is 0.5, so C to D is 0.5 of this negative 18.12. This is why I get it in here. So in the end, I have negative 9.06, and this one is 0. So in order to, in comparison of this, although I still have a this one, and if I distribute it for this, since this distribution factor is 0, so in the end, I will have a distribution factor of 0. So I have 0 in here. So all the line here, I have already 0, 0, 0, then I can stop. So in order for me to calculate how much is the end moment at the end of my calculation, I need to just take from here to down and sum up everything. So I have positive 10, 0, 0, 0, 0, 0. This is why I have positive 10. And now I have negative 73.3. So I have to plus this one, positive. And I have 0, 0, 0, 0. So this is why negative 73.33 plus 63.33, I have negative 10. And I have this one, negative 46.67. And I have positive, and I have positive, and I have negative. I sum all four, and I will have negative 27.8. And I have 45, positive, I have positive, I have negative, 0, 0, 0, 0. So this is why if I sum all the three, I have positive 27.8. And I have positive 75 and 0. I have this one, 0. I have this one, and 0. So I plus everything, I will have positive 66.4. So now this is my end moment due to the support settlement of the same beam. Now, once I got this end moment, the other procedure is going to be similar. I just need to plot my end moment over here. So this I have positive 10, negative 10. This is where I have positive 10, so it is clockwise direction, a negative 10, counterclockwise direction. And after that, I have a negative 27.8 for CB and CD positive 27.8. So I have negative, negative 27.8 and another one positive 27.8 for moment CD. And for moment DC, I have 66.4 positive. So this is why I have 66.4 positive, so it's going to be clockwise direction. Now what we do next is the same like what we have already done before. We are going to calculate the support reaction, because once you get the support reaction, then only you can calculate the then you can only prepare your shear force and bending moment diagram. So in order for me to calculate the support reaction, I have to just balance this reaction from the other end of my member to the support. So once I got the reaction, the VCB, the VBC, for example, the similar value will come on this end with different direction. Then after I have both reaction, I can get my support reaction over here. Okay. So let us see, it's not something new. It's good to refresh how to draw your shear force and bending moment diagram. So I do it first for member AB, and for member AB, I have a 5 kilonewton in here, and also a clockwise direction of moment in here. So easily I can calculate how much is my shear force for BA. So VBA, I use the simple static equilibrium, total F is equal to 0, so I have VBA equal to 5 kilonewton. And for member BC, I have a 10 kilonewton meter uniform distributed load. I have a counterclockwise direction of moment, 10 kilonewton meter, and I have a counterclockwise of 27.8 kilonewton meter of moment. And if I give the notation of VBC in this direction and VCB in this direction, I can easily find what is the value of my shear force for BC and CB. So I take first total moment at C equal to 0. So this one, in order to go to C, it follows the clockwise direction. So this is why I have positive VCB times the moment arm 4, and I have a counterclockwise moment, so it is negative. Another counterclockwise moment, so it's negative. And for this uniform distributed load, if it is acting on the midspan, in order to go to C, it follows the counterclockwise direction. So 10 negative times the length of my structure 4, and it is acting on the midspan of my structures, is going to be 2, because the moment arm is 2 over here. So if I solve this equation, I will have VBC 29.45, and using the total Fy equal to 0, I will have my VCB equal to 10.55 kilonewton. So the direction is going to be correct because all are positive values. For member CD, I have the moment clockwise direction 27.8 and another positive moment 66.7, and I also have a axial point load 30 kilonewton, and I notate it to be VCD this direction and VDC also pointing upward. So if I take a moment at D equal to 0, in order for my VCD going to D, it's going to follow the clockwise direction, so it's going to be positive. So positive VCD times 4, the distance. And for this one, in order to go to D, it follows counterclockwise direction, so that's why it's negative, and times the moment arm 2, 30 times 2. And this one is positive clockwise direction, so this is why I have positive 27 and another clockwise direction, so it's going to be positive 66.7. And if I solve this equation, I have VCD equal to a negative 8.63. So meaning the direction was not correct. The direction is supposed to be going downward. And if I calculate using the total Fy equal to 0, I will have a negative 8.63, negative 30 plus VDC is going to be VDC positive 38.63. So the direction is correct. And right now I have all the member shear force of the members. I have 5 over here. So this is valid 5. And I have also 29.45, 10.55. So this is why 29.45, 10.55. And after that, in order to balance these 5, I need to introduce another one shear force at the end of the at the opposite direction. okay, opposite direction, going downward 5, and to balance this one, similar amount, but the opposite direction, 29.45. To balance 10.455, I need to introduce 10.55 going downward over here, and based on my calculation, this one pointing downward, 8.63. So this one should be pointing upward, 8.63, and this one 38.63 pointing upward. So at the other end, I need to have something pointing downward, 38.63. So right now I have all the information I need for my support reaction for this one and also for this one. I can calculate them, and also for this one. Okay, so for this, since I have 66.7 clockwise direction, I need to introduce another one counterclockwise, 66.7, and to balance this one, I need to have another one clockwise direction. So I knew my MD is going to be 66.7 positive. So I have all the information for my support reaction. I can now draw my shear force and bending moment diagram. So I put here the reaction, support reaction, 34. 1.94, and also this one 38.63, and the moment. For this one, I do the continuous method. I don't separate my my beam into three members. So for this one, since it is pointing downward on the force, you have to remember, for shear force, positive is upward, negative is down from the reference line. So this is my reference line, and bending moment diagram, negative is on the upward and positive is in the downward. So now it is pointing downward, so I go down -5, because this one I have pointing downward, -5, and there is no force between A and B, so go straight. And from B pointing upward, 34, so -5 plus 34, I have positive 29, and this one going downward 10 kilonewton per meter, so 29.45 positive, I minus 10 times 4, so this is where I get this one. Okay, negative 10.55, and I have going upwards 1.94, so I have plus this one, so this is where I got this one. So this is wrong. Okay, this line is wrong, and there is no load between this point and this point, so I go straight. And another 30 kilonewton going downwards, so -8.63 minus 30, so I have -38.63, and there is no other load in between, so I go straight here, and from here going upward 38.63, so I go upward 38.60, so I just go back to 0. Be very careful if you calculate your shear force and bending moment diagram and you don't close it to 0, so go back to your calculation if you have time, in order for you to see where you've done wrong. Okay, now in order for me to calculate my bending moment diagram, it's also very straightforward. I just need to calculate how much is the area of my shear force diagram. So this one 5 times the length of my structure of my beam is 2, so I get -10, because it's negative. Okay, -10. And this one is 29.45, using the proportion rule. I have the length of this one 2.95, and this one is 1.05. So I just will get the area of my triangle, 1/2 times height over the length, so I got 43.4 positive. And similar to this one, since it's negative, I will have the area of -5.34, and this one area is -8.63 times 2. I have this one, and this is the area of 2 times 38.63. I have -77.26. So in order for me to draw it, since this is negative and it's in a straight line, so my slope is going to be a straight line. Okay, straight lines until -10, and this one -10 plus 43.4, so I go to 33.4 positive, and I have after that negative 5.35. So 33.4 positive minus 5.34, I got 27 positive still. And if I minus negative 17, I still have a positive 10.6. And after that, I have to minus another, the area is negative 77. So I go up to negative 66.6 something. And since this one, I have a clockwise direction of moment, 66.7. So plus 66.7, I go back to 0. So in order to joint my my point, this one is a straight line, so the slope is 0. This one is going to be straight, and this one is like a triangle, so it's going to be a slope a little bit, another slope a little bit, until I get here, and then it's a straight line, and then it's going to be a slide like this. So this is my bending moment diagram, and this is the negative, this is positive, and this is a negative. So if I want to draw the deflected shape of my beam, I just need to refer back which one is positive, which one is negative. Okay, so this one is a negative, this one is a positive, this one is a negative. So negative is a sad face, positive is a smiley face, negative is a sad face. So if I want to draw the deflected shape, it's going to be deflected a little bit up here. That is like that. Okay, so that's my deflected shape of my beam. This is the whole calculation for our example of beam. You can compare it with the one that you have already calculated for your assignment of the slope deflection method. Using the same condition of the support, you have the deflected shape also of your beam. Okay, do you have any question, class, for this one? No question? Okay, so if you have, if you look back, I think you will see that the moment distribution method is very straightforward. It's not too much complicated in terms of the application, but you need to first understand from which the value is going to be taken for your calculation in this one. Okay, and you need to also practice just to take this one direction to here, another one direction to that side, and in order for you to get familiar with the calculation. I have one example, example that I prepared for you for the moment distribution method of beam. And in this example, you have a continuous beam of two-span beam, which is supported by a fixed end at one end over here, and also a roller support, and also a roller support over here. So because sometimes some students, they say, okay, doctor, if we have a pin support, then for this one, we have a pin support, is going to be, okay, so if it is a pin support, it's going to be 3I over L, 4EI over L. So how's going to be if the condition we have a roller support, or what's the condition when we don't have cantilever? So and how's going to be the carryover factor if it is a roller support, or how's going to be the condition if there is no cantilever? So in this example, what I have prepared for you is the condition where there is no pin support, but instead of pin support, you have a roller support, and there is no cantilever. The end of the beam ended with a fixed end, and another side is ended with the roller support. Okay, you can see that the all procedures of the calculation is going to be the same. The steps that involve, you have to first calculate the member and the joint stiffness, and you have to calculate the distribution factor, you have to calculate the carryover factor, the fixed end moment, and you have to do the table, and you have to sum up everything. So if I can see here, I will go not too much slow for this example, because I prepared this in order for you to have comparison for your own sake, And I need you also to be familiar with the calculations. This way you can practice on your own and also to compare your calculation with the one that I have prepared here. Okay, since the moment distribution method is all about practice, you need to practice to calculate it very fast. You need to calculate. You need to practice to look into the condition, like, okay, in which condition you have to do your 3EI, in which condition is going to be 4EI, in which condition is going to be carryover factor 0, 0.5, and where you have to take it to decide left side carry over here or there. So I prepared this example for you to do your own and also compare your your calculation with the one that I have already prepared here. So this example is a complete calculation from the analysis until you come out with your shear force and bending moment diagram. The steps I also have indicated in here. The first one, you need to calculate your member and joint stiffness. Okay, so since this side is fixed, and this is your intermediate roller, and the N1 is your end roller. So for member stiffness is going to be for this N, 3EI over L, and the one close to the fixed end and intermediate roller is going to be 4EI over L. So the first step, you need to calculate what is your member stiffness for each member. So you have KAC, and also you have member CE. This is why you have KCE. After you calculate the member stiffness, you calculate the joint stiffness. So the joint stiffness is the total stiffness of all members attached to the joint. So for joint A, you have KAC and also the wall. So the wall is infinity, so you have the KA equal to infinity. For C, you have two members attached to it. You have member AC and member CE. So this is why you have this value. Similarly, for CE, for KE, you have KCE and also 0. Nothing attached, is only one member, so you have 0.75 EI. After you have calculated the stiffness member and the stiffness of the joint, you can easily calculate the distribution factor. Then after you have calculated the distribution factor, keep this value in your mind, that the total of the distribution factor for one joint, like for example this one, CA and CE, okay, CA and CE has to be equal to 1. Okay, this one has to be equal to 1. Now for the carryover factor, from fixed to intermediate, there is no carryover factor because fixed N is going to keep all the moment to itself. So this is why from here to it's 0, but from intermediate to N pin is 0 because N pin couldn't keep the moment at the end of the calculation. And after that, from N pin to intermediate pin is going to be 0.5. Intermediate pin to fixed support is going to be 0.5. So you have all the values that you have. And as for the fixed end moment, the equation, the procedure also is going to be the same. First, you need to determine the direction of deflection of your structure. So if I'm loading my structures 12 kilonewton per meter, like in this direction, definitely I knew that the deflection shape of my beam is going to follow this way. So I have this one. In order to push it back, I have counterclockwise FEMAC and also clockwise direction FEMCA. However, you can see that my load is only until the midspan. So this is a little bit new. We haven't seen it before. In your exam, you will be given this table. Okay, so in this table, you just need to see which condition is the loading of your member, whether it is point load at midspan, whether point load at a certain distance of the support, or this direction, or this shape. And in our example, we are in here. We are you have only your uniform distributed load at certain distance from your structure. So you just use this equation. Okay, so from this angle you just this equation, and another angle you have this equation. Take all this equation, put it in your calculation over here. So you will have your fixed end moment at an AC equal to negative 11 kilonewton meter, and another one 5 kilonewton meter. This one is very straightforward. You have already calculated so many times, and you will have your fixed end moment CE and fixed end moment EC to be this much. Now, just put your value inside the table. This one is the member, distribution factor, carryover factor, until the fixed end moment. Until here should be no problem. So right now for the joint A, C, and D over here. Sorry, I cannot see this one. E. So I have, in order for me to balance this one, okay, the distribution factor is 0, and for member C, I have 5 and negative 5, so I have to introduce a positive 20. So this is when it goes positive 20, distribution factor times this one, and this one distribution factor is 1. Okay, so I have negative 25 to balance this positive 25, so I get the negative 25 times 1 equal to negative 25. Now from here I have to carry over, right? So I can see my carryover factor is 0 from A to C, so 0. C to A is 0.5. So C to A, 0.5. From C to E is 0. So this is where I got 0. From E to C is 0.5. So this is where I got 0.5. Now I continue, I balance, I carry over, I balance until it goes 0. After I got 0, I just sum everything. I got this much. So from here, it's going to be all similar procedure. I draw shear force and bending moment diagram. I get the support reaction. So for this example, I do it member by member, because from this one I think it is a little bit tricky for you to calculate it for the continuous beam, especially because you have a moment in the middle of your span like this and this one. So for this I prefer to do it part by part. However, if you feel that it is more easy for you to do it continuously like the previous example, it's up to you. Okay, for those of your friend who wants to see the detailed procedure of your calculation of the support reactions, shear force and bending moment diagram, so I provided here for you the detailed calculation, and you can do it by yourself, and how you can get the distance of X. Also, I have also provided for you here. So do yourself a favor, go back and do the example from beginning until the end, until you get all the support reaction and bending moment diagram, and you can compare your calculation with the one that I have prepared over here, like how to get your maximum moment. And after that you can just draw and combine all the shear force and bending moment diagram for each members until you get the final drawing of your shear force and bending moment diagram for the example. Okay, so this one I just leave it for your self exercise. Please do so in order for you to get familiarized with the table and also the parameters, because next week we are going to do your moment distribution method for frame. And for frame it is a little bit more tricky because you will have sometimes more element. For beam, you can see here in one joint it is connected with 2 members, but in frame, in one joint, sometimes it can be connected with 3 members or 4 members. So when it happens, then your skill in order to carry forward to distribute it, you need to have better control and better exercise. Okay, so I give this example to you. Do your calculation.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.